Thanks very much to the organizers for putting together this nice workshop and for inviting me. So today I want to tell you about some work. The theoretical part of this was done in collaboration with Matteo Ippoliti, who is a postdoc at Stanford and has now started his own group at UT Austin, and Tibor Rakowski. And then we collaborated with the Google team to realize some of these ideas on their experiment. And really both the theory and experimental part of this was really led by Matteo. Okay, so over the course of this workshop, we've heard many interesting talks on the use of quantum simulators for useful information processing tasks. For example, the talk this morning was about using quantum processors for solving optimization problems like max cut. I'm a condensed matter many-body physicist, and the advent of these simulators have been equally impactful in many-body physics from a very different angle, in that these simulators have given us direct and controlled access to the dynamics of many-body quantum systems. If you're talking about an analog simulator, for instance, something like an ultra-cold atomic system, then the time evolution, the natural operational evolution of these devices is some type of time-dependent Hamiltonian, for instance, a Bose-Hubbard model or a Fermi-Hubbard model that could be representing the native interactions between the constituent degrees of freedom. And the simplest thing to do with these platforms is to start them off in some initial state and to evolve them under the dynamics that are intrinsic to the system. Okay. And of course, even when you're building digital devices to run the kind of random circuits that we heard a lot about, this is also a type of time evolution because you have a system and you're acting on it with unitary gates. So this is a discrete time evolution of a system, right? So now that we have controlled experimental access to the dynamics of many-body systems, this has led to, over the last decade, on many breakthrough results on universal phenomena that one can ask about and study in the non-equilibrium many-body dynamics. So for instance, this has shed light on many long-standing problems in statistical mechanics on questions such as many-body thermalization, quantum chaos, but also spurred entirely new types of questions in thinking about, for instance, new kinds of phases of matter that you can define in out-of-equilibrium settings, in driven settings, in ways that non-equilibrium or dynamical systems can evade reaching thermal equilibrium altogether, for instance, by using ideas from many-body localization or the topic of quantum scars, which is kind of a partial evading of thermalization. And these are important for thinking about new kinds of non-equilibrium phenomena that might arise, because if you just have some very unstructured, generic, random evolution of some many-body system, well, the expectation is that this is going to thermalize to some very boring state, right? It's just going to reach infinite temperature without any interesting correlations. So to talk about new, interesting non-equilibrium phases requires some way to evade thermalization to this boring state, and ideas like many-body localization have played an important role in that context, okay? So this has been a lot of very nice work, but really the vast majority of this work has focused on the unitary dynamics of systems treated in an approximation where they're perfectly isolated. Okay, we're just talking about completely isolated systems undergoing unitary evolution. But this is, of course, not the whole story by a long margin. When you open a standard quantum mechanics textbook, the two fundamental processes that you learn about are unitary time evolution, where quantum states evolve linearly, smoothly, deterministically through Schrödinger's equation, but also measurements, which causes wave function collapse and is this nonlinear, discontinuous, random process, right? And of course, the fact that we have these two very different sets of rules is the famous measurement problem, which I won't say anything about. But the point is that so far in many-body physics, all of our thinking on how to define phases of matter and characterize universal many-body phenomena has focused on this first setting of systems evolving according to Schrödinger's equation. And actually, much, much more, not even systems time evolving, but really just systems in their ground states or equilibrium states described by some time-independent Hamiltonian, right? And measurements really have played a very passive role, where you use measurements, you're given some state that you might be interested in, for instance, the ground state of a Hubbard model, and you think of measurements as this thing that you do to characterize the correlation functions of the observables or the order parameters in that state, but they're just useful for learning properties of states that you might have obtained through either unitary time evolution or equilibrium states that might exist for some interesting Hamiltonian, right? Instead, what these new devices, these new simulators have done now is to force us to also contend with measurements as an intrinsic part of the dynamics in their own right, okay? Because these simulators give us access to the dynamics of many-body systems, but they also give us very controlled access to be able to make measurements, process the data from those measurements, and then do controlled operations based on that information, okay? So, and the act of measuring a quantum system can fundamentally change the system itself, this we all know, but what this has done is opened up this area of many-body physics, which now goes under the name of monitored dynamics, where the role of measurements has been elevated from that of a passive probe to an active protagonist, okay? We're not going to think of measurements not just as passive, simple things that we do to learn about a state, but actually as operations that are going to fundamentally create new types of correlations and restructure existing correlations in the state, okay? So measurements are going to be a part of the many-body dynamics, yeah. Yes. Yes, exactly. And in fact, like the types of phases that I'll tell you about in a moment, it was initially thought of as a many-body Zeno effect. Yeah, that's right. Okay, so just to emphasize this point, you know, any type of quantum processor that you're building, the operation of this device is inherently a monitored, interactive, out of equilibrium quantum process, okay? And what do these words mean? Well, monitored is going to refer to the fact that I have controlled measurements, okay? I have an observer that is monitoring the system, which means that the observer is taking the measurement records, writing them down, and doing something with it. And this is in contrast to passive or uncontrolled measurements, which is just some environment that's always acting on the system. This is of course, decoherence and noise. This is not what I mean when I'm talking about monitoring or controlled measurements. But of course, all of these different effects are going to be present in the system, okay? There's going to be unitary gates. You can think of this as a driven system. There's going to be controlled measurements, which is necessary both for some output readout and in error correction for processes like detecting errors. There's going to be uncontrolled measurements due to environmental interactions. And then there's going to be the possibility of feedback, where you can process these measurement outcomes and then feed them back to determine the next layer of unitaries that you might be applying, okay? So as a many-body physicist, the question is, if you put all of these different ingredients together and think of this most general out-of-equilibrium quantum process, then what are new kinds of universal phenomena or new phases of out-of-equilibrium matter that we can think about with these ingredients, okay?
Question?
Yeah.
If I were to be smart and could use a noise model running for a certain time, would that also fall into your category?
If you could use a noise model running for
Running for, you know how long I want, on one part of the system I run a little bit of noise. Is that allowed?
Yes. So in fact, there are papers that are talking about, can you get a phase transition by tuning the noise strength?
Yeah.
Okay, and maybe you act on noise with noise and just, maybe if you're acting with bulk noise, then you just get something trivial, but maybe you're just acting with noise at the boundary, so people are definitely asking questions like that. And really the way to get noise is very simple. If you can do controlled measurements, just throw out the measurement outcomes, and then there's noise, right? So the controlled measurements is much harder than the noise is always there. Yeah. Okay. So as an aside, I'm not going to talk about error correction in my talk, but I want to also talk about I want to briefly just mention how measurements also play an important role in error correction. The standard picture that we all have for error correction is, of course, intrinsically that of an interactive process, right? You make controlled measurements of your error syndromes, you calculate some quantity based on this syndrome data, and then you can apply corrective operations, okay? So, and then, depending on what the noise rate of uncontrolled measurements is, you can get a threshold transition, which is a phase transition in a dynamical process, depending on whether or not you can correct these errors or not, right? So when you're thinking about error correction, the measurements are controlled, so they are monitored, the measurements of the syndromes. However, they're conventionally only used to deduce information about the errors, okay? That's what we're using measurements for. But very recently, there's been a lot of work on these Floquet codes, which really elevate measurements from probes to protagonists, okay? Again, because in this paradigm for error correction, the evolution really just looks like a sequence of measurements that you're acting with, and those measurements are used to simultaneously encode, correct, and compute. And the quantum information is encoded and operated on in space-time and not merely in space. And I'll emphasize the role of space-time later. Okay, so if you haven't heard about these codes, probably there have been talks on it, don't worry. But I just wanted to flag this for those who know that this active view of measurements is also really having a big impact on how we're thinking about devising new types of error-correcting codes. Okay, so today I'm going to be telling you about phases from measurements. So again, I'm thinking of measurements as being an intrinsic part of the dynamics. There's been a lot of work in thinking about adding structure to monitored dynamics, which have measurements. You can think of adding symmetries, topology, all sorts of ingredients. But the minimal model, the first set of models to be written down, were just that of a random unitary circuit, which you already heard about. So these are just unitary gates. They can be drawn from different ensembles. You can just think of them as being drawn from the Haar ensemble for simplicity. And then these unitary gates are interrupted by local measurements, which are made with some probability. Okay? So it's a minimally structured model that combines the ingredients of time evolution, unitary evolution, and measurements. And because you're constantly measuring and interrupting the system, you're preventing, or you can prevent, that's going to be the punchline, you can prevent this kind of boring thermalization to some unstructured state, and you can stabilize new types of non-equilibrium phases, which in this case will now be defined by the structure of quantum information in space-time in a way that I'll explain, okay? So I've used the word space-time twice now. And why am I talking about space-time? Usually when we think about an intrinsic phase, someone hands you a state and you measure correlation functions in the state. These are usually spatial correlation functions, or you can measure some topological feature of the state, but it's usually a state that's been handed to you, okay? But for these monitored dynamics, one of the things that we've come to realize is that it really is space-time that we care about. And the reason, one way to intuitively understand that is that when you have measurements, the arrow of time that you think about in conventional dynamics, this is really something that's well defined when you have unitarity. Okay? Unitarity enforces some conserved flow of information from the past to the future, and it defines this arrow of time. But with active or conditioned measurements, this arrow of time loses its special meaning, and space and time really become interchangeable. Okay, so a classic example of this is quantum teleportation, where if you have some shared entanglement between Alice's lab and Bob's lab, these labs can be very, very far apart, then Alice wants to teleport a state to Bob by making a measurement, again, a Bell measurement, and conditioning on the result of that measurement. Alice can teleport a state to Bob at an arbitrarily far away distance. Okay, so when you have these active conditioned measurements, this arrow of time loses its meaning, and space and time really can be considered as as interchangeable. Okay, so the phases that I'll be describing to you, they should be understood as in terms of distinct organizations of quantum information in space-time. Okay, and
sorry, can you tell me why it's losing meaning of the concept?
Oh, because you don't have a light cone anymore. So let me do an even more dramatic example. So suppose you have a whole bunch of different Bell pairs, okay? So this is a bunch of qubits all in a Bell pair state. And now you go in and you make Bell measurements on these pairs of qubits.
So you're referring to just the entanglement part or just the teleportation part?
Either. Okay, so if you go in and you make Bell measurements on these alternating pairs like this, you will have log2 entanglement between these two qubits, and this chain can be arbitrarily long, right? If you trace over what you got in all of these outcomes, then you recover your light cone. But if you don't trace over it, like with these active measurements, then you can entangle arbitrarily distant qubits with just one layer of measurements. So something like a light cone loses its meaning.
Well, usually light cone, we have just the meaning for, we just use it for the causal transport of the signals, right? Not really.
No, but there's a light cone even for entanglement. You cannot entangle
That's different light cone, okay.
Yeah, right? Because you can't, if I'm just doing unitary evolution, I can't entangle arbitrarily distant regions. But with measurements, you can. So that's the sense in which there isn't, yeah, okay. Yes?
I'm actually a little confused by what you mean by that, because I don't think you mean that we've somehow violated relativity.
No, you're not transmitting it. There's a telephone here, which is classical, or there should have been a classical telephone. You're not transmitting useful information faster than the speed of light. But if you're looking at this state, which you obtained by making measurements, right, these two qubits can be entangled after one layer of measurements. So things like, all of your usual intuition about how deep a circuit you need to run to get a highly entangled state, or even in log2 entanglement between two distant qubits, all of those should be thrown out the window when you're allowing yourself to make measurements. Yeah. Yes?
In this context, what is the significance of area law entanglement that you said the two?
I'm not talking about area versus volume right now. Any entanglement between, I can make this chain as long as you want. And I've done one layer of operations. And with one layer of operations, I've entangled arbitrarily distant chains. Whereas if you were running a unitary circuit to entangle arbitrarily distant points, not chains, arbitrarily distant points, even if you just wanted log2 entanglement between them, your circuit depth would need to scale with their separation.
I still have a problem if you say, time and space are not completely interchangeable. I don't know if you turn a picture around what the new gate would look like.
I'll get to that.
Not totally true.
No, it isn't, and I'll get to that. That was the point of several papers. Yeah. Okay. Yes. All right. Okay. So, all right. So allow me to be a little bit loose for a bit, and then I'll define what I mean by spatial, by this duality. Okay. So again, the picture that you should have in mind is that there's some spatiotemporal web of quantum information. I'm being loose about what I mean by quantum information, but the point is these models are so minimally structured. These are just random gates and measurements that I don't have that many observables that I can be talking about. Okay, so I'm talking about very, very, So for instance, one of the things that I'll use, the first thing that was used to characterize this phase transition that you're going to induce with measurements is the entanglement of the late time state. Okay, so you start with some input state, you make measurements, you act on it with unitary gates, and a picture is that quantum dynamics, these unitary gates, can build entanglement, okay? Whereas measurements can sever them, can build connections versus sever them, and then you're trying to ask, does this web remain connected, okay, as you keep going in time? So one diagnostic of that is if you look at some output state that you produce after this monitored evolution, what is the scaling of the entanglement in that output state? Is it an area law or is it a volume law? Okay, so that's one type of question. Another type of question connects with this thing I was saying about teleportation, which is, can you have correlations between causally disconnected subsystems? Okay, so suppose I run a very shallow circuit, so that if you didn't have measurements, there could be no correlations between this region there are your light cones, and there can be no correlations between things that are outside the light cone. But by making measurements, when you have this shared entanglement and you make measurements, you can create correlations between distant spins or distant regions of your state. So can you have correlations between these causally disconnected subsystems, which is a type of teleportation, okay? And that's one other diagnostic of a type of transition that you might get, okay? And something that will be very important in what I talk about is that I'm always going to be talking about transitions in individual quantum trajectories, okay? So the picture is you feed in some input state. You can take the all zero state for simplicity. It doesn't really matter because you have hard random gates here. You run this evolution. You get a lot of measurement results. You can call these M, okay? And then you have a particular output state conditioned on all of these measurement records, okay? And then you're going to ask about phase structure in this ensemble of trajectories, which is defined by psi of m, and the probability with which you obtain that outcome. That probability is just given by Born's rule, okay? And we're going to ask about a transition as something like the density of measurements is tuned, okay? Good. And, okay, I'm going to say that later. Okay, this slide is a little bit redundant, okay? But it's basically just showing you that there is this, that each time you make a measurement, you get multiple outcomes. So trajectory corresponds to one branching path like that. This is the phase transition we're going to be studying. And what was found is that if you take this output state that you get, psi m, and you compute its entanglement entropy, this is a pure state, okay? So you look at its reduced density matrix in some region A, you look at the entanglement entropy of that reduced density matrix, and then you average over all measurement outcomes, okay? So you're averaging the entanglement, you're not averaging the state first. Then what was found is that as this measurement rate is tuned, you get a phase transition from an entangling phase to a disentangling one, okay? Now, the two limits of this transition are easy to understand. When you have no measurements whatsoever, you just have hard random evolution, you get a volume law entangled state. That's natural. If you make measurements with probability 1, you're measuring out your state at you're making single-site local measurements in every layer. Then, of course, you get an area law state. There is no entanglement. And then what these papers found is that there's actually a finite PC where there's a phase transition from an entangling phase to a disentangling one, okay? So the way I said this, you might be tempted to just nod along and say, yeah, one limit is entangling, the other is disentangling. Sure, there's a phase transition in the middle, okay? But this is actually a very, very non-trivial result. Many groups thought about this question and then immediately said that there can be nothing interesting here. And the reason is that the presence of this entangling phase with a finite density of disentangling measurements is actually really shocking, okay? Because if you think about it, entanglement between, if you have some subsystem A and then the rest of A, and you're doing unitary evolution, entanglement is only being generated at the boundary between A and its complement. But you're making measurements everywhere in the bulk, okay, with some finite rate. So naively, you would think that entanglement is being generated at the boundaries and it's being sucked out of the bulk, so the bulk will always win. And then you might think that any non-trivial, a tiny, tiny, tiny non-trivial density of measurements, any finite small density of measurements should give you, sorry, I should have been pointing my pointer there, should give you an area law phase, okay? But this doesn't happen. So the persistence of this volume law phase is actually non-trivial and surprising. And this isn't just an ordinary volume law phase like you get with normal high random evolution. You can see that because there's these other corrections. There's this piece which is just an entropy density times a volume that looks like the type of structure that you would get if you just had high random evolution. But there are these universal subleading corrections here which actually point to additional structure in how the entanglement is arranged in these states, which make it robust to the presence of these measurements. Okay, so the properties of this volume law phase are not trivial and are quite interesting. Okay.
Is this mathematically related to the phase transition for graphs and population? The way, I mean, sometimes it becomes disconnected at a certain.
Yeah. So intuitively, that's right. The connection to percolation. In fact, this paper by Ruman, Nahum, and Skinner makes that connection. You can't really do it for von Neumann entropies, but for things like I think for certain Rayleigh entropies, certainly for this for the Rayleigh zero, it can be made precise. But the intuition is correct, but it's not exactly that for.
You have to work a little more.
Yeah.
So that non-analytic term is the precursor for transition. Is what you said? The 81/3.
No, that's there everywhere in this phase. And by the time you hit the transition, the leading term is gone.
Okay.
Yeah. Okay. Yep.
Sorry, how are you able to tell apart the entangling and the disentangling phases?
In one case, in the volume law phase, the entanglement scales with the volume of the subsystem. And in the area law phase, it scales with the perimeter of the subsystem. So that's a sharp distinction between them. But here I was pointing to additional subleading structure in the volume, in the volume law phase that shows you that it's a non-trivial volume law. Yeah.
Just out of curiosity, the critical probability there, PC.
Yes.
Is that something that there are analytical models that you can actually predict that exactly, or is it something that just has to be done through numerical measurement kind of estimation?
Yeah, no, it's numerical measurements. People are trying to develop some mean field-like understandings of these transitions. I don't know exactly what the status in that is. I know very recently there was a paper on trying to do this in tree tensor network type models, and there I don't know if it's exact or not. But generally this is non-universal and just numerical. Yeah. Okay, so all right, so let me, I should speed up a little bit. Okay, so the point is that the persistence of this volume law phase should be surprising to you. Okay, so don't take that for granted. And the way we've come to understand this entangling phase is again more in information theoretic language in terms of coding and learnability properties. Okay, so I'm not going to talk about it in detail. There's a very recent paper we wrote where we discuss this a lot in the language of classical shadows, which you might find interesting. But the question is just the following: Alice might have some initial state, which maybe she's encoded some quantum information into, and the point is that if your volume law is to be stable despite the presence of this finite density of measurements, what you want to be able to say is that the information that's there in Alice's state is encoded in a way that you can make these local measurements on the system, but the information remains encoded despite the presence of this density of local measurements. Okay, so this can be framed in the language in terms of this question, which is how much of the initial state that Alice has can she reconstruct if there's some eavesdropper Eve who's making measurements and writing down the outcomes of the measurements in her lab notebook. If Alice is given these measurement outcomes, how much of her initial state can she reconstruct? Okay, so this is like a coding or decoding problem because again, when you have, some error-correcting code, you're making measurements of syndromes. In that case, there's some separate noise channel, and you're trying to ask, can you learn information from your syndromes and be able to reconstruct your logical information. Here, your measurements are simultaneously playing the role of the thing that's corrupting your state and the thing that you can learn from, okay? The converse of this question is, if you don't have access to this final state, but you're Eve, and you only have access to the measurement record, then how much of Alice's initial state can Eve reconstruct just with her outcomes and without access to the input state, okay? So these are, again, two different complementary perspectives on this transition. And really, there's several, so the things that I talked about are, you can view this as an entanglement transition in pure state trajectories. You can view it as a teleportation transition, where again, this phase which has a dense network of quantum information has volume law entanglement, can teleport, can code and resist the loss of quantum information to measurements. It makes it hard for an eavesdropper to learn, okay? And it's also hard to simulate, okay? And the opposite side is this other phase. Yes?
Is this teleportating picture true also for bulk measurements? I've only seen the one by Ehud where they do it at the boundary.
No, it's also true for bulk measurements, because there's, I'll come to that. Yeah, hopefully that'll be clear. Yeah, okay. Good. So okay, so this is what I was saying. This entangling phase has this tightly connected web of quantum information in space-time, which allows all of these properties, whereas the disentangling phase has this loosely connected web, which leads to these failures. Yes?
So can you show the slide again with eavesdropping? Because I want to understand what's the role of the drive in this picture that you showed. Because if it were just the identity, then it doesn't matter if I spaced my measurements out.
No, it's not the identity. You have non-trivial gates, which.
Yes, exactly. But does it need to be relevant to the information I encode? Like, how does
right
how
now,
do those two interacting with each other?
Right now, I'm doing very minimally structured. I'm not trying to. I'm doing very minimally structured evolutions, right? So I'm not. These gates are just Har-random gates. The encoding can just be a Har-random unitary. I'm not even talking about. Yeah. So I don't know.
Maybe we can discuss it.
Yeah, okay. I'm not trying to encode some very special information that you need to worry about the structure of those gates for at this moment. Okay. All right. Okay. I'll just say that, understanding the properties of these phases in this phase transition is actually a very challenging question. It's not solved yet, or fully solved, I would say. But various approaches to doing this use this technique, which some of you might be familiar with, which takes random circuit models and maps them to effective statistical mechanic problems, and especially the entanglement in these random circuit models can be mapped in the StatMech language, and then this phase transition in entanglement ends up looking like a phase transition defined by spontaneous symmetry breaking in a space of replicas. Okay, so you don't need to. The things you should get away from this slide are the transitions that we'll be talking about show up in nonlinear functions of these observables. These are these rho A squareds. Okay, for instance, like an entanglement or rho log rho, and this requires multiple copies of your state rho. Which can be understood in this replica language, and this is one of the analytic tools that people use to study these transitions, okay? But I won't have anything more to say about this. So the thing I want to turn to now is the experimental challenge with trying to see some of this physics, okay? And the experimental challenge comes from the fact that this physics is really visible again, or most easily visible in these individual trajectories, okay? Because what the randomness of measurement outcomes means is that you're making a finite density of measurements at every time step, okay? Which means that your wave function is just branching and branching and branching and branching. So in order to to get a particular quantum trajectory, and if you want to get multiple copies of it, okay, that's just basically impossible, okay? Because if you run your experiment many times, you're never going to get this exact same sequence of measurement outcomes twice, okay? So this is what's known, and if you just average over all your experimental runs, okay, so if you just take these different branches and you average over them, you just get a trivial equilibrium density matrix, okay? That's like running this depolarizing channel. You can think of it like that. That's unital. This rho equilibrium in that case is just the identity. There's nothing non-trivial there, okay? So you cannot average over measurement runs. You need to look at individual trajectories. And the point is that in any quantum simulation experiment, you obtain expectation values by taking a shot of your experiment and then getting one answer and then doing it again and again and again and again. But this requires you to prepare that same state many times, okay? Because if you just run your experiment many times and keep getting different measurement outcomes and you naively average over them, then that's like passive decoherence and you don't see anything, okay? So if you were trying to measure just some expectation value like you would do in a conventional experiment, which is, you have some observable, you measure it in your trajectory, and then you average over all trajectories. This is like averaging this observable over this equilibrium output state, which is averaged over all measurement outcomes, and that just gives you 0, okay, because that's trivial. On the other hand, nonlinear quantities, for instance, the entanglement entropy, which have multiple copies of psi, this can give you a non-trivial expectation value, okay? And since probably lots of people in this audience work on spin glasses or have thought about it at some point, this is analogous in some ways to this Edwards-Anderson autoparameter, where if you just take a simple expectation value and average over disorder, you get 0. But if you look at some kind of squared expectation value, then that can give you something non-zero, okay? Good. So as I said, measuring these requires preparing many copies, but the quantum randomness of measurement outcomes presents this fundamental post-selection barrier and gives you this exponential sampling complexity, which is exponential in the space-time volume, which is naively really makes this an impossible problem to observe experimentally. Okay, so the different experimental challenges are this fundamental one that I just told you about, which is about the randomness of measurement outcomes. No amount of quantum engineering can solve this problem for you. Okay, this is just fundamental to the nature of quantum mechanics. But then there's also two kind of near-term challenges. One is that mid-circuit measurements are currently quite costly. Okay, they cost about 10 times the gate time in terms of coherence. And also that you always have environmental noise or uncontrolled and passive measurements. And if your system is getting entangled with the environment, that's a trivial volume law phase, and you can't tell the difference between this. You can't probe the transition you're trying to probe. Okay? So this was viewed as theoretically interesting, but perhaps, just theoretically interesting. But then there was a lot of recent work where we were able to observe this unobservable, so-called unobservable phase transition. So I'll tell you about some of the approaches we took in this recent paper, and it builds on these two prior experimental efforts, where the main thing that we added to those was a way to address this fundamental post-selection problem. Okay, so those prior papers, they showed how you can see this on small systems where you can still kind of deal with the post-selection by brute force, but now we came up with a different kind of order parameter that allows you to go beyond that, okay? All right, so what did we do to overcome these challenges? The first conceptual thing we did was the space-time duality mapping, which allowed us to move all measurements to the final time and remove the need for mid-circuit measurements. So even though we were effectively simulating monitored dynamics, we were able to restructure the measurements in a way that they were all made at the end. Okay, so that helped this, and in some cases, it also ameliorated this post-selection barrier. Okay, down exponentially, actually ameliorated it. Okay, the second thing we did was that we used noise as a feature rather than a bug. We came up with a way to to use noise, the response of the system to noise in the two different phases as an order parameter. And finally, we devised a hybrid quantum classical order parameter similar to this cross-entropy benchmarking parameter that Google used, which combines the data from the quantum simulation with data from a classical simulation. Basically, you need two copies. Okay, I said you need two copies of the wave function to see this. We just use classical simulation to give us the second copy. Okay, so this, instead of discarding the wrong outcomes, this is a way to basically fix them and do a decoding. The bad thing is that this replaces this post-selection cost with the cost of classical simulation. Okay, so there's no completely free lunch, but it still allowed us to push this system from being observed on systems of order 10 qubits to 70 qubits, which is what we did. Okay, so this was like at the limit of what we can, more or less at the limit of what you can do with classical simulation. Okay, good. So I'm going much slower than I thought, but because that's okay. So what is space-time duality? As I was saying, this gives us a flexibility in embedding a given monitored evolution in physical space-time. And some of these embeddings can be used to move all measurements to the end of the circuit. Okay, so what you would like to do is an evolution like that, where you have unitary gates, measurements, and that's your output state. What you can show is that in some cases, you can move it, you can take this for a particular class of monitored evolutions, not every class. For a particular class, you can arrange it in this way in which you make unitary evolution, measurements at the final step, and then you move the state that lives on this time-like slice. You just think of this as some tensor network, okay, as your output state, okay? And this state will have undergone monitored evolution. In another picture, which is much more general, and any monitored evolution of 1 + 1 dimension can be viewed in this way, can be restructured in this way. You have a shallow 2D circuit. Time goes in this way. You make measurements at the final time. And this 1D chain that lives, that's unmeasured at the end, has effectively undergone bulk 1 + 1D measurements. Okay? So I haven't explained any of this to you, so I'll just give you one slide on this. Okay, so suppose you have some unitary gate. It has 2 input legs and 2 output legs, and time goes in that direction. Okay, so that's unitary. Now I'm going to just declare a different dual time that's going from left to right. So I'm going to view these two, O1 and I1, as my inputs, and O2 and I2 as my outputs. This is just going to be a permutation of your original unitary, but generically that permutation is going to be non-unitary, okay? And in general, you can show that this can always be interpreted as a post-selected measurement. Why post-selected? Well, because you had one unitary gate, and if you dualize it, you get some one operator, okay? And that operator is a particular non-unitary evolution. So the simplest example is if your unitary is the identity, which you can write like that with your word lines going in that way. When you take its dual, you permute the various indices, and you get this other, U tilde that you get looks like a post-selected Bell measurement, where that's the Bell state that we're talking about. Okay? So that's great, but then of course, a thing that you'll ask is, okay, so then what do we want to do? We want to say that, I want to view my state as running in this particular way, okay? So I have some set of unitary gates, but I want to view it as time going from left to right, okay? As my input state being fed in there and my output state being obtained there, okay? So a natural question you could have at this point is, that's fine, this is a post-selected Bell measurement, but how do you actually do that in the lab, right? It's not like in the lab you have a gadget which allows you to apply this operator. The way you apply it in the lab is to make a Bell measurement and discard. Okay, so what have I actually solved for you? What I've solved for you is that by just rearranging how this circuit diagram works, which I won't have time to tell you about, you can basically use some set of ancilla qubits, some network of swap gates, and this network of swap gates is just taking the state that lives here and moving it there, and making one final round of post-selected measurements. And by doing this, this state that you get here, this psi out, is exactly this state that lived on this time-like slice, which underwent monitored evolution in this direction like that, in the space-like direction. Okay, so all of these are things you can do in the lab. You can prepare an initial state as a product of Bell states. You can run unitary gates. You can run swap gates. You can make a final set of post-selected measurements. And then the state that you're left with is a state which morally has undergone monitored evolution. Okay? This is a very specific class of monitored evolutions because they come from non-unitary operators that are dual to unitary operators. Okay? And that's one example. Let me skip this part. What we showed here is that by taking different classes of temporal dynamics in unitary evolution, we can map it to different types of scalings in this monitored evolution for the final state. And this also actually helped us explain some of the features of this non-trivial volume law state that I had alluded to previously. Okay? Okay, so then we did this on the Google chip, okay, where these are my qubits, these are my extra qubits, these are swap gates, these are actual gates, these are post-selected measurements, that's my output state, and I want to know the spatial scaling of this output state, okay?
Is converse also true? Can you view the non-unitary circuit into
No, not always. So it's very special non-unitary circuits that are dual to unitary ones, okay? And then I measured the Rainey entropy of different subsystems of this 12-site system. And what we found is that, okay, here, let me just go to the next slide. What you want is something that's going from entangled or volume law, because you want this entropy to scale with the subsystem size and then come back down, right? Because 12 is the entire system, to being very weakly entangled, and for various technical reasons, this is logarithmic rather than area law, okay? So you do see these two different qualitative behaviors by tuning the families of unitary gates that we have in this evolution, okay? And to get this, we had to do some error mitigation, because you see that by the time you're looking at the entropy of all 12 sites, this really should be 0 because it's the entire system which is supposed to be pure. So your unmitigated data had some entropy there, which was coming from the environment, and we just did a very poor man's error mitigation where you just get an entropy density corresponding to this final state, subtract that out, and then that gives you a curve which is much more sensible, okay? All right, then we wanted to go to 2 dimensions, and there, any 1 plus 1D monitored evolution can now be written as an effective 2 plus 1D circuit with measurements at the final step and this final unmeasured state right here, okay? And the way to think about this is really that you're viewing you're thinking, because it's a finite depth circuit, you have an effective 1D state that you can think of as being contracted in the space-like direction again, and that is again giving you an effective monitored dynamics for this one-dimensional state right here, okay? So the number of gates, so question is, what is the effective measurement rate, okay, when you have something like this? And the number of gates, this is a very hand-waving argument, but it is true that this is what tunes the density. The number of unitary gates that you have is Lx times Ly times the depth time. The number of measurements in this case are being made only at the end. And this gives you a measurement density which scales like 1 over t, okay? So this, by tuning this depth of this 2D circuit, you are getting a transition from an area law to volume law, but it's a transition of an effective 1 plus 1D monitored dynamics which is this unmeasured state right here. Okay, and what this paper by Aram Harrow showed is that because of this 1 plus 1D effective transition that we have, this can also be viewed as a phase transition in the complexity of simulation, because if it's volume law, then you would imagine that that's hard to simulate, okay? But this is an experiment that Google can do very, very easily, because this was their standard experiment. It's just a 2D circuit, shallow unitary time evolution, and then measurements at the final step, and then you're asking some properties about that wave function, okay? Good. So now we did this first with brute force without doing the clever tricks. So if you're doing brute force, we were limited to 19 qubits. We did measurements on 12 of them, and you had 7 left over in this edge. So, so this is kind of what it looks like. You make these, you tune the depth, you have some entangling gates, you make measurements at the end, you have that final state. Then you ask about the entropy profile of that final state, now as a function of circuit depth, okay? And as a function of circuit depth, you see that, well, somewhere between 3 and 4, okay, this behavior seems to change, okay? I can't really tell you this is discrete, can't really tell you exactly where a transition is, but somewhere between less than 3, this looks pretty unentangled, and greater than 3, it looks very entangling, okay? So good. And then you can also do things like measure the mutual information between distant qubits, and once again, as a function of circuit depth, you find that it goes from very little mutual information to large mutual information between those end qubits. Okay, so all of this kind of checks out and is consistent with some transition between 3 and 4. But we would like to scale this up. Right now, we did brute force, which means we actually did post-selection. Okay, so we ran this, we got some set of measurement outcomes, and we kept doing this over and over again, discarding runs till we didn't see the same outcome twice. Okay, so it's a brute force post-selection, and it's brute force obtaining the entropy of 7 qubits, which is actually also not completely trivial. Okay, the entropy of some region scales with, getting that entropy scales exponentially with the size of the subsystem. Okay, now we want to scale up. We actually want to go all the way to 70 qubits, which at least at the time of the experiment was the largest chip that they had. I don't know what it is now. And what we also wanted to do was have access to this transition more in a more resolved way, okay? Because we don't want to say just that we're seeing something between 3 and 4. We want it to be more, we wanted a continuous parameter. So what we did is we just fixed the depth to 5. And we tuned the probability with which we were applying gates in each layer. Okay, so that's this gate density rho. This gives you an effective depth, which is rho times t, and you get a phase transition as a function of this rho, as this gate density is tuned. Okay, good. So what are the problems that we're going to encounter when we scale up? There's 2, okay. The first is post-selection, which I told you about. Okay, you're now going to measure a whole bunch of other qubits. How you're going to deal with post-selection. And the second is more benign, which is just the cost of measuring entropy, okay? Like if you want to distinguish between volume law and area law entanglement, and you now have a much larger effective 1D chain, well, then the cost of measuring entropy itself scales exponentially, okay? The second problem, Mike Gullins and David Hughes had solved for us already. What they said is that, well, if you entangle a probe qubit into your monitored dynamics at the early step, at step 1, and then you run your monitored evolution, all you have to ask is, at the end of your monitored evolution, is your probe qubit, does it remain entangled or does it get disentangled? Okay? If you had this dense web of quantum information, the probe qubit would remain entangled, and if you didn't, it would get disentangled. So this only requires measuring the entanglement of 1 qubit, which is cheap, but it's still the entropy of 1 qubit conditioned in the measurement record, which is costly. So now I'm going to solve this problem for you. Okay? Actually, before I solve it, I'll just tell you about the experimental setup. It's not so important to entangle one at the beginning. You can just do like a slight variant of it where, again, you have this 2 plus 1D system. You run it. You choose some probe qubit here. You run a short time evolution. And then you measure these qubits and ask about the entropy of that probe qubit as a function of how many of these qubits you've measured, okay? And as you keep measuring in this direction, this is really like playing the role of dual time, okay? Because like space is like is like time for this monitored evolution. So I'm going to keep measuring, and I'm going to ask about, does this qubit remain entangled or not? Okay, so the post-selection problem can be stated as follows. The entanglement of this probe spin is quantified by the length of its block vector. If you just look at one spin on the block vector, if it's on the block vector, then it's pure. Otherwise, it's yeah. So you want to obtain the length of this block vector, but the problem is that if you randomly average the block vector over different trajectories, each trajectory has this probe spin pointing in a completely random direction. So then this will average to 0. What you want to do is, again, use something like multiple copies to average the square of this vector, okay? But that's a challenge. How do we do that? And we did that by just getting these two replicas through a classical simulation, okay? So essentially, your quantum device gives you a final output state and a measurement record. On your classical computer, post-selection is easy. You just apply you apply projectors onto the measurement outcomes that you encountered, get the same trajectory out, and then you can measure this kind of hybrid quantum classical order parameter where one of the copies is coming from your experiment, one is coming from your classical simulation, and then you can average over all runs and still be okay. Okay, so that was the key step. I'll skip. Okay, I have 4 minutes. All right. So you can show that this ends up looking like a kind of decoding. Okay, it's like basically saying something like, before averaging, you're trying to flip to always be on the North Pole so that when you average, you only get the length and you don't wash out. Okay, but don't worry about that. The upshot is this protocol where you have some experimental bit that you measured, which is plus or minus 1. You took your measurement record, you ran it in your classical computer, you got a block vector on your classical computer, that gave you another plus or minus 1 sign for you to average, and then you can show that this gives you, when averaged over measurement runs, this gives you this quantity zeta, which looks like an expectation value of the absolute value of the block vector, which in turn is related to the entropy of the block vector, or of that probe spin, okay? Good, so this is sample efficient. We're not throwing away any run, okay? We're using every run, and you pay this classical simulation cost, but you can do 70 qubits exactly, okay? And again, this idea of these hybrid parameters has been used in different contexts, most notably in this cross-entropy benchmarking, where you classically obtain a probability from a classical simulation of a given bit string. That's what this M refers to, and then you average that over your quantum runs, okay? So this has also been, this was used previously as well, or something related to it, not exactly this, of course. Okay, so then, good. So the last thing I want to tell you about is the impact of noise. Okay, so what all have I solved? I've solved the problem, or Gullens and Hughes solved the problem of trying to measure the entropy of a big state by saying you can use a single probe state. We solved the big issue of the post-selection problem. I think that was one of the biggest conceptual things that we did, which was different, by using this hybrid quantum classical order parameter. And now, in the last minute, I want to tell you about what we did with the effect of noise. Okay, so if you just look at the entropy of this probe qubit, suppose you measure all the other states except this probe state. Okay, if you were exactly in a pure state and you measure everything and you're left with just one qubit, well, that's a pure, in a pure state, that will be a pure state of a qubit, okay? So the length of that block vector should just be 1. Instead, what you find is that you see this exponential decay of that zeta, which is coming from the effect of noise, okay? Everything is also getting entangled with the environment, so your probe qubit is not in a pure state, and this deviation is a signal of noise. So first, we did the simple thing, which is just divide zeta by this decaying envelope. You get something close to 1. This is, again, the poor man's mitigation, analogous to what we had done previously. And then this allows you to get a mitigated entropy. We use that to get a finite size kind of crossing for the experimental data to estimate a phase transition around rho of 0.9 between something that was disentangling and something that was entangling. Okay? But what we found is that there's this drift in this crossing as a function of system size, which is a signature of instability to noise for this problem. Okay? So instead, we decided to use. Instead, what we did is decided, this is my last slide, we decided to use noise as a feature rather than a bug, okay? So the point is that when you have this tight web of quantum information, then when you have noise, this probe qubit feels the effect of noise everywhere, okay? So then its deviation from just 1 is scaling exponentially with the entire size of the system. On the other hand, in the disentangling phase, this probe qubit is only sensitive to what's happening within some correlation length. So then this deviation is not scaling with system size, it's just finite. So actually, if you look at how this zeta scales with system size, what you find is that in this disentangling phase, which is this low rho, you see very little system size dependence. And then by the time you're in the entangling phase, this depends exponentially on system size. Okay, that's shown here. And in the middle, there's this broad crossover. Okay? And then in this StatMech analysis, in this replica picture, this noise actually acts like a symmetry breaking field, like the susceptibility of a magnet. So you can actually understand the order parameter's response to noise in this nice way, and that sharply characterizes those two phases. Okay, so we're now using noise as a feature rather than a bug. And that's my summary, which is we're basically trying to elevate measurements to active components and asking about the new types of non-equilibrium phases that we can get. The paradigmatic example of this is this entanglement phase transition as a function of measurement rate. And we addressed various NISC-era experimental challenges in trying to observe this on this large system of 70 qubits.